Yes, Fred, you're excited about learning about LP spaces, aren't you? That's right. Well, we're going to do that next. What's that, Slopey? No, you don't have to pee to do LP. Good. Um, anyway, let's get right away. Yes, polar bears start with P. Yeah, that's good harmony. All right, let's get ready to go. Well, first, we want to do Lebesgue integrals of complex valued functions. If f is a complex valued function, the values, not the inputs. F of x equals u of x plus iv of x, and that's real, and that's real. And this part is called the real part of f, and this is called the imaginary part of f. Okay, that part. And the way you define the integral of u plus iv over some set A, it's just the integral of over A of u plus the integral over A of v. It times out. And then you get a number that's complex numbers. And then, yeah, I guess I should say union infinity. Sometimes that happens. All right. So we let L1 of, sometimes you put L1 of R to be the set of all functions f such that the integral over R of the absolute value of f is less than infinity. So this is the same as the script L, the Lebesgue integrable functions, but now we're allowing this to be complex valued. And then this means the complex absolute value. So in other words, 3 plus 4i is the square root of 3 squared plus 4 squared equals square root of 25, which is 5, for example. But anyway, but you can do that at each point x in R. So, and then we could also do Rn, same thing. Again, it's only the output that's complex value. And then similarly, for numbers p between 1 and infinity, yes, Fred, I know you like p, good. All right, I thought that was Slopey, you liked that before. Anyway, this is you can define LP, which again we can do LP of Rn if you want, like that. And you can also pick or A at some measurable set somewhere. That could be another way to do it. But then that's just the domain of the functions. So you can put anything there. Anyway, I'll just define it using the Rn version. And then this would be the set of all, oh, I forgot to say that this is measurable. Yeah. The set of all measurable functions f, well, otherwise you wouldn't know what to do with the integral, such that, let's see, that the integral over Rn of s value of f to the p power is less than infinity. Yeah, and just as a note, this is a lemma, is that f in m implies that absolute value of f to the p is in m. We proved this for p equals 1, but it's higher in higher p's. It also works. And then also, in this set, we use the equivalence relation, just like we have sometimes done before. F squiggles g if and only if f equals g almost everywhere. So outside a set of measure 0, two functions are equal, then we call them equivalent. And yeah. And if I change that to a different set, A, I would just put an A there. But otherwise, it would be the same. And then also we say L infinity is the set of all F measurable such that F is essentially bounded. So it's kind of like almost everywhere bounded. And what does this actually mean? So I'll tell you in a second. Let me just tell you first of all, the P norm that goes with an LP is this. You actually do that integral absolute value of f to the p power, and then you raise the whole thing after integrating to the 1 over p. And then the infinity norm of a function f, well, it's the sort of like the soup of the function after subtracting off a set of measure 0. So what the heck is this? Well, actually, you have to write it as the nth of this, of a number m such that f of x is an absolute value less than or equal to m on Rn minus some other set S where measure of S equals 0. So this is the nth over all possible f. So this is, yeah, this has to be true. So it's kind of like an upper bound, kind of, but you can subtract off sets of measure 0. It's really complicated, but yeah, you just ignore sets of measure 0 and it's the soup of the function. Kind of, it's really what it is. All right, now what about these LP spaces are important? Well, maybe you guys might want to ask about the LP spaces. Like if I start a theorem, LP of Rn is A, what might you come up with? That's right, Hermione. Yes, yes, that's right. It's a vector space. Fantastic. And there's even more that we're going to be able to say about that. But first, we have to do a little bit of analysis. All right, so let's do that. Well, here's a lemma. And this is just a real number lemma. For all x and y in 0 infinity, x times y is less than or equal to this gizmo. If p and q are in the interval 1 to infinity, and 1 over p plus 1 over q equals 1. And these are called Hölder conjugates. The p and the q that satisfy that. And by the way, you're pretending that 1 over 1 plus 1 over infinity equals 1, because it can actually be infinity. Yeah. So that's a very crazy inequality there, but amazingly enough, if this equation is true, it works. So, but I'll mention a little bit about the proof of that a little bit later. Now, I know you want to see the proof of it now, Red, but you know, we sometimes just have to wait. Okay. Yeah. It's tough for Fred sometimes waiting. Anyway, all right. So here is the amazing theorem called Hölder's inequality. So suppose P and Q are again in 1 close bracket infinity, and 1 over P plus 1 over Q equals 1. Okay, so they're Hölder conjugates. Then suppose F is in LP and G is in LQ. Then, this is the conclusion, F times G is in L1, and the L1 norm, which is just the integral of the absolute value, is less than or equal to the LP norm of F times the LQ norm of G. So it's a really cool fact. So let's do the proof here. Well, first off, there's a simple case if F or G equals the 0, or I should say squiggle 0. 0, it's 0 except for a set of measure 0. Then what happens? That's right, Hermione. Yeah. If F or G squiggles 0, then we get equality. Because let's say F is 0, that would be 0, and that would be 0. And then if G is 0, that would be 0, and that would be 0. So, yeah, so that's good. All right. Otherwise, using the lemma, let x equal be changed to f of x over the p norm of f, and then y changed to g of x over the q norm of g. And those are just constants, right? So then we get this equation, the absolute value of f of x right here, right? Actually, I think I want absolute value. Yeah, let's put absolute value. Okay. Then we have absolute value of f of x, g of x, divided by the p norm of f, q norm of g. And I guess I could put absolute values there around the whole thing. And it's less than or equal to, so that's this part. So this one would be 1 over p times absolute value of f of x to the p divided by the p norm to the p plus 1 over q times the same thing with the g and q. Okay, so that's from the lemma, using the lemma. And we get that. Now, integrate both sides. And we get, well, those are just constants, so I'll pull them out. And then the integral of absolute value of fg is less than or equal to, I'll pull the constants out, 1 over p norm fp to the p, which is times the integral of absolute value of f to the p, plus 1 over q norm g q norm to the q power times the integral of absolute value of f to the q, and I could integrate over Rn, or I could integrate over some of our other set. It doesn't make any difference. And notice, oh, this is G, sorry. Yeah. And notice this is the same as that. This is the same as that. So it's 1 over p plus 1 over q, and that equals 1. So therefore, you get that this, which is just the 1 norm, of fg is less than or equal to the multiplying by this constant, and you get it. So that's the Holder inequality. Really cool stuff, huh? Don't you think it's cool? Yes, it is cool, right? And what else did you want to say, Slopey? Yeah, you would have liked this better if it was an equation of a line, because then you could calculate the slope. Yeah, that's a good point. Good point. All right. So before we talk more about that, let's go ahead and have some results about the LP spaces. So the proofs of these things are in the book. I'm just going to state the results. That's the main thing I want you to remember. So remember, we said that this is a vector space. Well, now it's a normed vector space because if you take the P norm, it is a norm. You can check all of the different properties. Positivity, yep, that definitely works. And because where's the P norm here? Yeah, it's in that previous page. Yeah. So this number is always positive, so yeah, positivity is true. And then if this equals 0, that means the inside equals 0. That means this is 0 except on a set of measure 0. And then that means f is 0 except on a set of measure 0. So you get positivity, and then you also get constants come out correctly. That's why you have to take the 1 over p power, because otherwise a c times f would come out as c to the p times f in absolute value. But with that, it works. And then the triangle inequality, that's also has to do with some little bit of analysis, but it works, like the lemma and everything. So yeah, so that's cool. Next fact is that LP is complete for 1 selection of P less than infinity. Yeah, this is also for 1 less than P less than infinity. So that's great stuff. So remember what this means. This means that Cauchy sequences converge to elements of the space. Yeah. And yeah, so that's really good stuff there. And again, the proof of that is in the book, and it's similar. Both of these capital LP spaces are similar to LP spaces, which are spaces of sequences. LP is the set of sequences AN such that the sum of AN to the P power is less than infinity. And see how that's similar. The sum becomes an integral. That becomes a function of x instead of n. So it's kind of a similar deal. Oh, yeah, and you need absolute values there too. Right. And then I wanted to also tell you a couple of important things about the LP. First of all, a step function is it's a simple function. Let's see, S equals summation ck chi ek. K equals 1 to capital N. All simple functions look like that, where that's the characteristic function of the measurable set ek, such that the measure of ek is finite for all k. So simple functions you can actually have sets of infinite measure in here, but not with a step function. Anyway, there's a theorem that step functions are dense in LP. And in fact, step functions are always in every single P, and they're dense in every single one of those. And then last but not least, L2 is a Hilbert space. Complete inner product space. So it's an inner product space where the L2 norm is the integral of f g bar. Right. And we've seen that before. And the L2 norm is exactly the inner product norm of this L2. That's it for LP spaces. Isn't that exciting?